In this section we found out that the fundamental theorem of algebra says that every polynomial of the type that we've been studying, but now with complex coefficients, has at least one complex zero. So the worst case scenario would be that you would factor it as x minus c to the n power. Of course there'd be an a out there. But this would just have one zero because it's of multiplicity n. So that would be the worst case scenario. So in any case, there is always at least one. The complete factorization theorem says that we can factor any polynomial into linear factors. So each of these is a linear factor because the x in there is degree 1. So we use all the techniques that we've been studying to find all the zeros of a polynomial. And the zeros of a polynomial are just the values of x that make the polynomial equal 0. So we take the polynomial in the first instance, x to the 4th power plus 4x squared, set that equal to 0. And so we factor x squared as a common factor. And now we have x squared plus 4, which in the complex numbers we can factor, because in the complex numbers we have I. And so the sum of two squares can be factored in this way. And so this is equal to 0. And so now we have a 0 of multiplicity 2 at x equal to 0. So x equal to 0 is a 0. We have a 0 of multiplicity 1 at x equals 2i, and another 0 at x equals negative 2i. Notice that the complex zeros are conjugates. So counting multiplicities, we have 4 zeros. And we factor the polynomial completely. We remember that if c is a 0, the number c, then we know that x minus c is a factor. So we have 3 numbers here to substitute for c. The numbers are 0, 2i, negative 2i. Therefore, p of x, our polynomial, can be factored as x squared minus 0 times, or just x minus 0 squared, times x minus 2i times x plus 2i. And that's the complete factorization of that polynomial. Now for the next example, we are going to factor again, but first let's clear the page here. So factor this one again, we have a common factor of x. So this polynomial is x times x squared minus 2x plus 2. Now that can't be further factored, and so we find the zeros by, well, let's just complete the square. We already know that 1 0 is from this factor here. We have a 0 of x equals 0. So we have 1 0 right here. Now we're going to solve x squared minus 2x plus 2 equals 0. Let's just do complete the square. So we have x squared minus 2x equals negative 2. Half of 2 is 1 squared is 1, so we add 1 to both sides. And we have x minus 1 squared equals negative 1. 2x minus 1 equals plus or minus I, because the square root of negative 1 is I. And so x equals 1 plus or minus I. So now we have 2 other zeros. We have 1 plus I and 1 minus I. X equals 1 plus I. X equals 1 minus I are the other 2 zeros. So remember, if c is a 0, then x minus c is a factor. And so the factors of p of x are 0 is a 0 of multiplicity 1, so it's x, times, well, I'm going to actually need a higher order. Do it again. The important idea in this section is that you can always factor every polynomial into linear factors. and that if you count multiplicities, you'll have the same number of factors as zeros, which is the same as the degree of the polynomial, and that there's always at least one complex zero. So the worst case scenario would be if you factor it and you had something like this, where you had exactly 1 0, but it was of multiplicity n. This is supposed to be a right here. So that's the worst case scenario. You just have 1, but there has to be at least 1. So now we'll factor our polynomials completely over all the complex numbers. So this one, we'll factor it by finding its zeros, because once we find a 0, then we'll know we have a factor. So we take the polynomial and we set it equal to 0 to find its zeros. We've always done. To find the zeros, you set it equal to 0. Now you factor x squared times x squared plus 4 equals 0. And so we get x squared times x squared plus 4 is x minus 2i times x plus 2i. And that equals 0. Remember, x squared plus 4 equals 0 is only if x squared equals negative 4, and that's x equals plus or minus the square root of negative 4, which is 2i. So x equals plus or minus 2i, and that's where I got these x minus 2i and x plus 2i. And notice that now I have actually the factors of the polynomial, because now I know that p of x is equal to x squared times x minus 2i times x plus 2i. And the zeros are 0 of multiplicity 2, 2i, and negative 2i. Those are the zeros. 0 is a 0 of multiplicity 2 because of the x squared term, or the x squared factor. Okay, so the next one, again, has a common factor. So we'll factor out the common factor, which is x. So we have x times x squared minus 2x plus 2, and we're finding zeros, so we'll set that equal to 0. The factor x gives us 1 0, x equals 0. The next factor is x squared minus 2x plus 2, we'll set that equal to 0. X squared minus 2x plus 2 equals 0. This one we'll do by completing the square. X squared minus 2x equals negative 2. Half 2 is 1, squared is 1. I have to add 1 to both sides. Now I have x minus 1 squared equals negative 1. So I'm going to get complex solutions. X minus 1 equals plus or minus I. Square root of negative 1 is I. Now we solve completely, get 1 plus or minus I. So those are two zeros right there. So we factor p of x. First factor is x. From the 0, x equals 0. Next factor is x minus 1 plus I. Forgot to write the 1. 1 plus I. And the next one is x minus 1 minus I. It's getting a little tight right there. And so that equals x times, now in here I'm going to use the distributive property and simplify that. So I get x minus 1 minus I. And in the second one I'll do the same thing. I'll use the distributive property and I get x minus 1 plus I. Like that. So there's the factored form of the polynomial. So here we have a polynomial to factor completely, and the zeros theorem tells us that we have exactly n zeros counting multiplicities. So we're going to look for 4 zeros for this polynomial. I can actually factor this polynomial. Let's see, x to the 4th power plus 2x squared plus 1. I can factor that as x squared plus 1 times, x squared plus 1. I set that equal to 0, so x squared plus 1, of course, is factorable as the sum of two squares. That's x plus I, x minus I. But the other x squared plus 1 has the same exact factorization, so I actually have x plus I squared and x minus I squared equals 0. So I see that I is a zero of multiplicity 2, and negative I is also a 0 of multiplicity 2. So counting the zeros, I have 4 zeros of this polynomial. And in fact, in factored form, I can write q of x is equal to x plus I squared times x minus I squared. So here are just some examples of polynomials of various degrees and how many zeros each one has and what the multiplicities of each one are. So you can study this table, and I'll just walk you through finding all the zeros of this polynomial. It's a polynomial of degree 3, and if I want to find some zeros, I'm going to use synthetic division, and I'm going to look at the possible rational zeros. And since the constant is 8 and the leading term is 1, the possible rational zeros are just the factors of 8. So we get plus or minus 1, 2, plus or minus 3. I mean, not plus or minus 3, what am I thinking? Plus or minus 4, and plus or minus 8. So we'll try these and see if any of them give us a remainder of 0. So first we'll try 1, the coefficients 1, 2, 4, and 8. And we see that we get, well, actually, it's not going to work because no matter what happens, I'm always going to get positive numbers. I'm just having positive numbers and I'm adding positive numbers all the time. So I know that none of these positive ones are going to work. So let me just try negative 1 instead. So 1 times negative 1 is negative 1, plus 2 is 1. 1 times negative 1 is negative 1, plus 4 is 3, and that's not going to give me 0. So now I'm going to try negative 2. Negative 2. 1 times negative 2 is negative 2, plus 2 is 0. That's going to give me 0, plus 4 is 4, times negative 2 is negative 8. So there, I found a 0. I found a 0 at negative 2. And now I've reduced the degree to the degree 2, so these are the coefficients of x squared plus 0x plus 4. Now I can just factor this because I know that x squared plus 4 factored is x plus 2i times x minus 2i. And so that gives me the two zeros, positive 2i and negative 2i. So 2i and negative 2i are my other two zeros. So I have one real 0, and I have two pure imaginary zeros for a total of 3. So I found all the zeros of this polynomial. To the conjugate zeros theorem, where if a polynomial has a complex number for a 0, then it also has its complex conjugate for a 0. And we can use that to find polynomials given information about the degree and about the zeros. So a degree 3 polynomial, it has a 0 of 2, therefore I know that this polynomial, p of x, if it has a 0 of 2, it means it has a factor of x minus 2. It has a 0 of I, so a factor of x minus I. And by the conjugate zeros theorem, it also has a 0 of negative I, so x plus I is a factor. So what you should do now is multiply this out. I'll let you do that on your own time for practice. I would suggest that you multiply these two first. That'll give you a nice binomial product. And then multiply that times x minus 2, and you'll see what polynomial you get. So the idea is to factor completely. So here is a polynomial we can try and factor completely. In fact, I know that I can factor this as x squared, let's see, plus 9 times x squared minus 1. If I set the factors equal to 0, I can find the zeros. X squared plus 9 can be factored as x plus 3i times x minus 3i. X squared minus 1 is the difference of two squares. That's x plus 1 times x minus 1, and that equals 0. So I have 4 zeros. I'm supposed to factor it and factor it completely into linear factors. So there it is. It's factored completely into linear factors.